Hello everyone, and welcome to the fourth video in our Class 6 session of instructional lecture videos. We're finally beginning Chapter 4, and we want to start off this video by asking why is all this conformational energy diagram making important? Well, it lets us see that certain conformations are very different energetically. And this is important, as you'll discover if you take biochemistry, in that for many enzymes, the proteins that get chemical reactions in biological pathways to occur, many of them function in the sense that they put a molecule in a strained or more reactive conformation, and this is only altering its conformational energy by a few kcals per mole, but this allows the enzyme to catalyze the reaction, so the reaction happens, and it's really quite elegant. So differences in conformational energy are even more pronounced in cyclic alkanes than they are in our linear alkanes, and like I said, we'll use the butane as a model for understanding some conformational energy systems in cyclohexane chair conformers. But first, let's consider burning stuff, because this is chemistry and we like fire. Consider burning pentane and hexane. So here we go. There's pentane, 2 molecules of pentane reacting with 16 molecules of diatomic oxygen, generating 10 molecules of carbon dioxide, 12 molecules of water, and 838 kcals per mole of heat. If we burn a couple molecules of hexane, we also generate carbon dioxide and water and consume oxygen, and we release 999.8 kcals per mole of heat. So what is that extra CH2, that extra methylene, worth? Well, it's about the difference in heat between those two reactions, so that's 161.8 kcals per mole. On average, so this was just the difference between pentane and hexane, you could imagine an average energy for burning an extra CH2 among many different examples. It actually comes out to about negative 157.4 kcals per mole. All right, well, that's interesting. So what? So let's look at a nice cyclic alkane case. Let's consider burning cyclopropane. Well, there are 3 CH2s. They're all arranged in a ring. And so we might calculate what that would be worth. It would be simply 3 times negative 157.4 kcals per mole on average. So our calculated energy released from burning cyclopropane should be negative 472.2 kcals per mole. But when we do this experiment, we actually get out a little more heat. We get out negative 499.8 kcals per mole. This is quite a significant difference. The difference between experiment and theory is about 27.6 kcals per mole. So where is that extra energy coming from? Well, the answer is called ring strain. So the cyclopropane system is a very strained molecule. If you remember from geometry, triangles' angles have to add up to 180 degrees. So if we have a triangle whose sides are all equal, we would expect a 60-degree angle between any 3 carbons in our cyclopropane molecule. We know that carbon in the sp3 hybridization state prefers to have bond angles of 109.5 degrees. So we've significantly compressed that natural bond angle, and like a spring, we've stored energy in that cyclopropane ring. So that's where we get the extra 27.6 kcals per mole energy, because as we burn cyclopropane, the ring opens and it releases that stored energy. Additionally, all the hydrogen atoms in cyclopropane are eclipsed. Here is a little bond line-like diagram for cyclopropane as best I could draw it, and you can sort of see that the hydrogen atoms would be eclipsed. You could try building a model with your molecular model set, but I imagine that your model, you might break some bonds there. All right, so cyclopropane, we've covered that. What else could we do? We could look at cyclobutane. So consider cyclobutane. It has a ring strain of 26 kcals per mole. The ring can pucker slightly to relieve some of the torsional strain. This is highly exaggerated. You could actually build a model of this without breaking plastic bonds with your model set, and you can see that the pucker is very slight. How about cyclopentane? Cyclopentane has a ring strain of about 6.5 kcals per mole, so we've dropped significantly by adding one additional carbon. And cyclopentane adopts a semi-envelope-like conformation, not exactly as drawn here, but this gives you an idea of what you might see for a cyclopentane molecule if you could view the world in X-rays. If cyclopentane were planar, all the hydrogen atoms would be eclipsed, but like I said, it's usually in this envelope conformation. So I guess I'll end today by going ahead and building models so you can see what a grown man looks like playing with plastic toys, living through his second childhood with you guys. So let's see. We want to do a cyclobutane, but I seem to be just taking my models apart. There we go. Gotta remove a hydrogen. Wow, these molecular model bonds are pretty tight. So here's cyclobutane. You can see there's strain, right? Because now we're disobeying that 109.5 kcals per mole. We're making our carbon-carbon bond about 90 on the interior of that ring. I said that this pucker is a little, well, like I said, it was exaggerated in my drawing, but here we go, right? A little forced puckering of my cyclobutane ring. And we could all believe that, yes, if we increase this ring to accommodate yet one more carbon atom, then we relieve that ring strain. And so we gotta pluck a hydrogen off here, put in another carbon-carbon bond. Here we have cyclopentane. This is interesting. So like I said, cyclopentane can adopt a envelope-like conformation. In reality, it's probably a little twisted, more like this sort of envelope to avoid eclipsing hydrogen-hydrogen interactions. But we still have a little ring strain, 6.5 kcals per mole. And when we get to cyclohexane, we begin to see some interesting things in terms of conformation. Nature really loves six-membered rings. They are found in great quantities in natural products and drug molecules, so we will pick up there in our next video.